Okay. Hi, hello everyone. It seems we are live, so I'm pleased to welcome you to the 8th edition of Functional World. My name is Matylda.kaminska and I'm responsible for employer branding at Scala. And today we have two speakers. One of them is Aleksander Rainko, who will be the first to talk about ducktape. And the title of his presentation is Holding Scala's Productivity Together with Ducktape. And then we'll go to Maciej Gorywoda's presentation about cellular automata for video games in JVM. And well, I'm very happy that we can be here together today. And I would like you guys to introduce yourselves. So maybe let's start with Maciej, who is our guest today. If you could tell a few words about yourself.
Yeah, hi. Well, in my day-to-day work, I'm a product marketing manager in the Scala plugin team in JetBrains, which is a long name for someone who takes care of their web page, Twitter, and communication with customers and other companies. I try to keep in touch with programming still, at least in my hobby time. So that's why today I will be talking about something connected to my hobby project about Cellular Automata.
Okay, thank you, Maciej. So now we can go to Oleg. If you could introduce yourself.
Hi, my name is Aleksander. I'm a Scala developer at Scala. Basically working on your everyday backend Scala jobs. And I'm here to present you my little talk about Scala's productivity, maybe more about ducktape, the library that I maintain, and then something about how that can be plugged together with some tools from the Scala ecosystem to make for a very nice and productive workflow for everyday needs.
Okay, perfect. Thank you, guys. So now I think we are ready to start with the first presentation. But let me just say that we encourage our viewers to ask questions in the chat, and our speakers will answer all of them right after their presentations. So, Oleg, let me know if you are ready.
Yeah, let's go.
Okay, so we are all ears, and good luck.
All right. So, holding Scala's productivity together with ducktape is the title of the talk of my talk. So let's go through an agenda first. So the agenda. I'm gonna go up on a quick round about JSON APIs and how Monday they are to program and do every day. I'm gonna introduce you to ducktape and what it really is, what it does. I'm then also gonna introduce you to the idea of IDLs and CodeGen in general, and then we'll see how we can put it all together for some like really nice benefits for us and less headaches. All right, so the story. Moving JSON from socket A to socket B pays the bills. That's the harsh truth of software development. And for example, in my pretty short career, about 4 years now, like 50% of the job, maybe even 60 or 70, was just creating REST endpoints with JSON bodies, which got pretty mundane really quick. So yeah, they are. It's also really mundane. So I want to go through a list that I came up with that encapsulates what we need to do to create a REST API in Scala, probably in other languages as well. So first of all, we probably want to have a root definition with a DSL of your choice. By DSL, I mean HTTP for us, ACK HTTP, Zero HTTP, whatever really. Right. So there's always some code to write to describe the structure of the endpoints that we want to have. But then we also want to model the request and responses of those definitions. So for example, we can always imagine that each of our endpoints probably has a body that it takes in or spits out. So for example, if I want to create a person in my database, I create a post endpoint with a person with a JSON body. For example, we can imagine that person has a name and a last name, right? So two very specific properties that we need to expect. So we need to model it, which usually in Scala, that usually comes down to creating case classes and then writing some more code for the JSON deserialization and serialization logic for them, usually in the form of semi-derivation of encoders or decoders of your JSON library of choice. Well, then with our API model in place, we probably also have a domain model. So our domain model is the thing that is really, really well defined with all the business rules in place, with a lot of invariants that need to hold throughout the whole flow of the application. And that usually means that our domain classes are usually protected with a private constructor with some validation rules, parsing or sanitization in there, right? So it's not as easy as just passing the properties to the domain model. We also need to run the validation function there, which probably returns an either or a string, usually, right? And we need to handle those errors and then surface those errors to our API users to know what they messed up, basically. So yeah, transforming the API model to the domain model is also usually a lot of work because it's mundane, it's mechanical. It probably should be automated in some way. Then, before we go on to actually expose the API, do anything really with it, we probably should document that, because how good is a design? How good is a contract that is not written anywhere, right? So we need to make a pinky promise to our team members that we won't break that API, and that pinky promise usually takes form of Swagger documentation or maybe something else, right? So, and then we also need to keep updating that documentation with each change that we make to not break the API for our consumers, because otherwise everyone will be mad at us, basically. But then we are free to apply the business, so we can run our database queries, whatever we want. We can do whatever we want now, because we went through all of this. We can now go on to the task that we want to actually solve. But what if we didn't actually have to? What if you only had to do this? So you would only ever document the APIs that you want to create, and then you do your business thing, and that's it. That's literally it. So documentation will be so the source code will be the documentation, and you wouldn't worry about anything really, because then you're just talking about in your business domain language. So how do we do that? So I split that into two parts. First of which is introduction to ducktape, and that will help us solve the problem of transforming API models to our domain models. Okay, so what is ducktape? Ducktape is a macro-based library for automatic and configurable transformations. What I mean by that is given two case classes with the same, for example, given two classes with the same fields, and yeah, exactly the same fields, we can use ducktape to automatically transform between those two, so we don't have to write the boilerplate ourselves. That may sound like Chimney to some of you. So yeah, ducktape is heavily inspired by Chimney. But what is Chimney? Well, Chimney is a Scala library for boilerplate-free and type-safe data transformations. So sounds pretty similar, but ducktape is a slightly different take on the ideas presented in Chimney. And what's most important, ducktape is a .t exclusive. So while Chimney doesn't yet have a Scala 3 port, I believe that's in progress right now. Ducktape only works on Scala 3, doesn't work on Scala 2. What that means for me, I get to use all the nice macro niceties and don't have to worry about Scala 2, right? So yeah, so what is ducktape made of? Well, it's more or less made of one type class. There's more type classes there, which I'll go on to explain later. But the most important one is transformer. So what is transformer? Transformer takes two type parameters, so source and destination, and has a single method, and that method is transform. So we take a transformer with a transform method. That transform method takes a source and then splits up the destination. What that means is that we can say that this transformation cannot fail. It's total. It can only ever fail at compile time, really. So but failing at compile time is completely fine, right? We don't need to worry about that. So yeah, transformer is the primitive that everything else is built out of. In ducktape, there are instances for the most common transformations available out of the box. So for example, transformations between collection types. We can imagine we can transform between a list of string and a vector of string for free, and that's what the ducktape gives us. There's automatic derivation for case classes and enums, so really the meat and potatoes of the whole library. As an example, so yeah, here I've got two sets of case classes. One of which is tag. So a tag has a presenter, it has a pitch, and it has a name, it has a pitch, and it has a presenter. And the presenter itself is also a case class with some more fields. So our presenter has a name and a bio. All that's a string, doesn't matter really for now. And there's tag2 and presenter just to show off how it works. You can see that the field order doesn't matter. That's what I wanted to articulate here. So the field order doesn't matter as long as the name of the fields are the same. So with ducktape imported, we get access to some syntax. To is one of the syntax methods that ducktape brings in. And what is to? Well, to takes to materializes a transformer from the source type, so talk, to the destination type. So tag2 in this case. And for example, it will just create it will basically create a transformation for us automatically. What that gets expanded into is this. So that's literally the code that the macro generated that I just copy pasted from my editor. So yeah, we can see that a transformer instance gets created for us for tag2 to tag1 to tag2. And what it looks like is it just invokes the public constructor of tag2 while copying over the fields from the first talk basically. And the same goes for presenter. So as you can see, nested transformations are also supported. They do not generate new allocations of transformers. And that's all taken care of for us. So that's basically the code that I would write by hand, really. So there's also a derivation for enums, as I mentioned. It's pretty basic for now because it only ever works with singleton cases and only when the case is mapped by name, right? So we don't get any niceties with really complex GATTs or something like that. So for example, here, I created two enums, one of which is an event type that has two cases, on-site and an online. And then conference type, which has three cases: on-site, online, and hybrid. Right. So once again, with ducktape, I can say that I want to transform my event type, on-site in this case specifically, to conference type. And the code that gets generated is just this. It's literally a if-else statement that matches on the type. And if the type has the same name, it will return the same name from the other enum. So that's really it for coproducts. And the general rules for derivation for case classes are as follows. So automatic transformation can be created for case classes. So this, just get back to it, can be created given that the source case class has all of the fields of the destination case class, name-wise, I mean the names, and the types corresponding to those fields have an instance of transforming scope. So, and pretty much the same goes for derivation rules from enums, but it's more limited, as I said. So so given that a source enum contains a subset of destination enums cases, once again name-wise, and all of them are singletons, then the transformation can be generated automatically for us. Okay, but what if the fields don't perfectly match? Because most often than not, our domains differ slightly, but differ probably with some fields missing or some fields added, right? So, for example, I created another set of case classes. So this time it's a person with a person has a first name and a last name, and a serious person which also has a first name and a last name, but also has a social security number abbreviated to SSN. Just transforming that just transforming a person into a serious person won't work. We'll get this at compile time. So the compiler will yell at us that there's no field name SSN from the person. Well, what gives? What can we do? We can try nudging the derivation in some way and telling the compiler to don't worry, you get this field covered, for example. So to create some kind of a builder of transformations, I like to call it, we use into. What is into? Into is another syntax that is brought in by ducktape, and that creates a builder of transformations of sorts. So I just say that person into serious person, and then I create the transformation itself. And then there are a couple of transformation options available for us. I believe now there's like 5, but only 3 of them, are the most basic ones that you use every day. For example, so the first one is field.const, and here you pick the field that you want to configure, quote unquote. And then what const means is you give it a constant value of that type of that field. And then there's also field.computed. Once again, you pick the field. And what computed takes in is a function from, in this case, from person to the type of that field. So a function from person, to string in this case, because SSN is a string, right? So I take a first name from person and then append SSN to it, whatever the value of first name is. And then there's renamed, which is a less powerful thing than computed, really, because you just get to rename the field. So for example, here we say that in place of SSN, the last name will be used, basically. Okay, but that only ever works if the constructor of the case class we transform into, so the destination case class, has a public constructor. And once again, more often than not, our domain classes have private constructors, right? So because we don't want them to have invalid state, so they probably do some validation or something like that. So yeah, what if it has a private constructor? So once again, we're greeted with a person and a serious person, but this time serious person has a private constructor, and also serious person has a smart constructor that returns an either of string, so some validation going on there, or the serious person. Well, what can we do? So in ducktape, there's also via. What is via? Via expand. You can think of via as expanding the parameter list of the passed-in method. So for, in this case, serious person create with the fields of the source case class. So once again, I try to right now I try to expand serious person create with the fields of person, but the compiler once again yells at me that there's no field named SSN from the person, because as we can remember, person only has a first name and a last name, and the create method takes a first name and a last name and an SSN. So we get a compile time error. So once again, how do we fix it? Well, just as there is into for configuring transformations between types, we can use into via to configure transformations between a type and a method expansion, rather, right? So in this case, I say that I want to create a builder of transformations for method expansions, rather, and then I get to use pretty much the same configuration options as in the first case. The only change is that we change field.dat to arg.dat, but they basically work the same. So arg.const, once again, we pick a field, and then we apply a constant value to that, and sorry, not a field, and we pick an argument of the method and apply a constant value to that argument. I computed, once again, we pick an argument and then apply a function from the source case class to the type of that argument. So for this case, we once again get the first name plus SSN, and renamed pretty much the same as the last time. Okay, but what about more sophisticated examples of case classes where where the fields themselves have validations. So it's not as simple as just writing for example, new tag or new presenter inside, but you also need to take care of first creating the components really. So first creating the fields, and then going through all the, for example, go through a flat map chain to get there. So once again, the answer is yes, sort of. But to actually show a good example, we need to hear about IDLs and generated code first. So that segues me to the next part of the presentation, and that is the introduction to IDLs, aka interface description languages. So an example of an IDL is OpenAPI. Maybe first, what is IDL? So IDL describe contracts between different services, whatever. And OpenAPI is a YAML-based IDL for describing REST APIs. So it's declarative and focused on a single thing. It has code gen support for every possible language under the sun. I'm pretty sure if it has a compiler or it runs anywhere, it probably has a code generator for OpenAPI. It has great Scala support in the form of guardrail. And it's basically your source of truth for both implementers and consumers. What that means is, if I were to expose a OpenAPI spec to my consumers, to my team members, for example, and I generate code from that OpenAPI spec, I cannot ever, maybe I can in some cases if I try hard enough, but generally I cannot break the contract that I created, right? So what makes up a OpenAPI file? It's YAML, as I said, but it has paths. An example path is /conferences for creating new conferences. We can see that it has well-defined request body in the form of a reference to something. I'll show you that in a second. And each of the endpoints that we define here has well-defined responses. So we can say that the /conferences endpoint with the post method will always ever return a 201 with a description of conference successfully created, whatever, or a 400 with some validation errors inside. So what's next? The object definitions themselves. So for example, create conference, first referenced here, has 3 properties, name and city, which are strings, and it also has a date span. And date span is another object, and a date span has 2 properties, a start and an end, both of which are strings, but formatted in a way that a date is formatted, which gives a hint to the code generator to use a type that supports dates, for example, local date in Scala. Once again, there's another object, validation errors, which is a simple object, a wrapper object around an array of strings with the errors inside. Yeah, so all of that's cool, but what does this really give us? So first of all, it gives us, in terms of Scala, of course, it gives us the API model. So you remember the create conference object just from the slide before. That's what Guardrail would generate for us. So it would generate a case class called create conference with 3 fields, name, date span, and a city. And it also generates encoders and decoders for that type. In this case, it uses sourcey because I used the HTTP forest generator for those examples, but it also supports AKHTTP, drop wizard, and then also there's also support for Java if you like Java. Yeah, so that's the first file. It also generates, of course, it generates case classes for all the other objects of date span, once again, and validation errors, once again. And it also generates the really, really unfun part of what I mean by the unfun part is the root definition itself, or the serialization and deserialization logic that you need to write by hand, which is probably more often than not error prone, and let's be real, it's really mundane to write. So yeah, so we get that for free if we generate the code from the API spec. So yeah, right here also generates it also generates the response models. So responses are modeled as sealed abstract classes. So for example, for our create conference endpoint, there's created, which is a case object. And there's also bad request because we return A400, right, with the validation errors inside. And then it also generates the actually useful part. What the handler trait is our hook into the generated code to actually use the well-defined body of that endpoint. So by the time that gets actually invoked, we are past all of the mundane steps, really. So we are past serialization, we are past actually matching the root, we are past everything else that we want to have, probably some middleware, whatever, authorization maybe. So as you can see, the only thing we need to do I need to do as a implementer of the API, I need to implement that handler object. And then which basically gives me the ability to start with my business logic right away from here, right? Right, but sorry. So that's cool, but where's the API model to domain model transforming part? All of that was part of guardrail, by the way. But right now, what I might mention is the API model to domain model transforming part. So that's and usually what I mean by that is transforming to domain models that have validations inside or whatever. So ducktape also has something called fallible transformers. So as the name implies, a fallible transformer is a transformer that can fail, basically fail at runtime. So they come in two flavors. There's accumulating transformers and fail fast transformers, right? How does accumulating transformer look like? So it has three type parameters. So it still has source and dest, but it also has a abstract wrapper type of f, a hierarchy type. And what that f means, it's a wrapper type of the transformation. So we can imagine that f is option or maybe f is either, right? But fallible transformers also have another thing. So to actually make use of fallible transformers, we need to know something about the wrapper type, and that's where the support type classes come in. So the support type classes define options that the macro needs for invoking fallible transformations. So in case of accumulating transformations, the support type class only has three methods. It has a pure method. Pure basically means lifting a value into that type. So for example, if f is option, then pure would be just calling sum, right? It has a map method to actually modify the contents inside the wrapper type. And for accumulating transformations, it has product. And what that signature means is that each transformation is independent from each other, and they can all fail at the same time. And we can accumulate all the errors from them. Hence the name accumulating, right? So there's also fail fast transformations for when we want to bail at the first state of trouble, which has the same signature as accumulating transformation. So there's a source type and a destination type and the wrapper type, right? But the support type class differs slightly in the sense that we exchange product for flat map. And flat map usually, when you see flat map, you usually know that we are about to enter the area of short circuits, basically. So what that means is the transformations depend on each other, and if one of the transformations fail, all of them fail, basically. So we can't proceed without all of the pieces. That's my headcanon, basically. With fail fast transformers, we only get the first error that occurred, and rest of the transformation is short-circuited, right? Okay. And then something more about fallible transformers. So they support a superset of total transformers config DSL. By total transformers, I mean the normal transformers that can't fail. So the ones that I showed off first. With two, so it supports field.const, field.computed, and field.renamed. But there's also two more variants to that. So it also supports field.fallibleconst, which is just like const, but we supply a value that can fail, and that becomes a part of the transformation. And fallible computed is just like computed, but it can, once again, it can fail, right? So instances for fail-fast transformations with options and eithers as result types are available out of the box. And accumulating transformations for eithers with iterables on the left side are also available out of the box. But you're, of course, if a user, you're free to define your own instances of support for the types that you need. And we can also think of fallible transformers as a superset of total transformers in the sense that we can always lift a total transformer into a fallible transformer by using the pure method on the support type class. And there's also fallible transformers also have automatic derivation for case classes with pretty much the same rules as in the case of total transformers. So once again, all of the fields need to match. What I mean by that is all of the fields from the source type need to be from the destination type have to be in the source type, and all of the fields when the names match and the types between those fields have to have an instance of a fallible transformer of some sorts in scope. For accumulating transformers, it will be accumulating transformer. For fail-fast, it will be fail-fast, of course. But that also entails that we've got to model our domain model a certain way, and that certain way, and by that I mean we want to have we want for our fields to have invariants baked into the type system. So we basically want all of our fields of a case class to be a new type, and that just means that we want to use new types, right? In Scala tree, because we operate in the context of Scala tree, we can define a new type library, quote unquote, in like 10 lines of code. So with the help of new types, opaque types, I can define a new type with validation. I use right here I use refined to define some validation logic where the A is the wrapped type and the constraint is the constraint on that type. So a new type also has a smart constructor. So we take a value of A, so the type being wrapped, and then we run it through the validation that refined gives us, which spits out an either of list of string or that type or that specific type, right? And then once we get the make method, we can expand that make method into our accumulating transformer, just like that. Once again, it uses refined for validation and source code to extract some useful metadata for nice error messages. So that what I mean by source code is the library that thing here that provides us with some metadata for our fields for nicer error messages that get reflected here, but doesn't really matter right now. And each new type will have an instance of transformer that accumulated in implicit scope. So that's the rule of automatic derivation that will be given to us for free if we model it that way. As an alternative for validation, we can use iron in Scala tree and Marnix new types for a complete implementation of new types. Let's go on to actually modeling the domain model and showing off what we can do. So in the case of a conference, how would I model a conference? So I will model a conference as a case class, of course, which will have a name, which has a new type over a string. So this thing, there's conference name, there's date span, and there's city. But what are all of those things? What are all of those things? Unsurprising string is a type alias for a string refinement that is always trimmed, is non-empty, and with a max size of something. We specify the size here, right? So now we define a new type called name, which will be a string, and that string will always be trimmed. It will be always non-empty, and will have a max size of 20 in this case. City is literally the same, and there's also date span. Date span is not a new type. Date span is a case class of its own. which once again has two properties, start and end, but it has a private constructor. But we also define a smart constructor for datespan, right? So we can't create a datespan that has a start date after the end date, basically. Okay, so now that we've got the domain modeled with new types, we can put it all together. So once again, going back to the handler trait that is generated by guardrail, I implement it with a class, whatever. I also created a conference repository that I didn't show you, but you can imagine that it has a single method. That method is create, which takes the domain conference, right, and creates a database. Doesn't really matter what it does. Only matters that it takes the domain. It takes the domain conference. So our target here is to transform the body. So the API that create conference thingy created by the guardrail into the conference, into the domain conference. And as you remember, the conference has fields that require validation first. So what accumulating transformers give us is a really shorthand way of creating such transformations. So once again, I want to transform the body, so create conference into a domain conference. So I just say body into conference. I then enter the accumulating transformation builder with this. That's all. Once again, that all comes from ducktape, of course. I need to specify the type, the wrapper type. So in this case, it would be either of list of string or the thing on the right. And then I actually invoke the transform method. And the transform method I need to nudge that transform method in this case, because as we remember, datespan doesn't have a public constructor. So I need to create a way to transform the datespan from create conference from the generated model into the domain model of datespan. I can do this. I can do that with valuable computed. So I pick the datespan field, and then by using via, I expand the datespan.create method with the fields of this, which completes the transformation, at least at compile time. So yeah, in case of errors, I just return body request with the validation errors. If everything is all right, I just invoke the create method on the conference, which then invokes the database, whatever, right? So what that gets expanded to, by that I mean this thing. So the transformation, it gets expanded into something like this. That's all macro generated. Once again, I just copied it over from my editor. So that's really what ducktape does under the hood. So in the case of transformation of accumulating transformation, because we do accumulating transformation here, it gets expanded into a chain of calls on product. So we can see that with each product call, we get a new member of the tuple appended to it, or rather prepended to it. Prepended to it because it's left associated. We invoke the transformers for the valuable transformers for name and city here, and also that's how via expands in here, right? That's the logic that expands the via call to datespan.create. But then it gets mapped with this. So first of all, there's a map call over all of this that transforms the tuple that we get from multiple product calls into actually the type that we want. So a value of tuple 2 datespan conference name, that type, and conference city type. The macro will create a match expression that distracts that tuple into something like this, and then invokes the constructor of conference with the values inside. As for this, that needs to be here due to a dotty-bug for now. So if we create a match expression with macros, it doesn't have exhaustivity checks. I filed that bug, but it's not fixed yet. Hopefully someday. But yeah, basically that's what the macro does. Okay, but does it actually work? All of that work, but does it actually work? So you can imagine that somewhere in the background, I started a server with the trait, with the handler, and I run a curl onto the endpoint. So onto the conference endpoint with a post method. And the body of name with an illegal conference name with over 20 chars to break the validation for that. Invalid date span, because those two dates are not, so start is not before the end, strictly speaking, and city with a really, really long name. And the request and the response that I will get is invalid date span, start is not before the end, blah, 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 for all the others. So what that means is the macro-generated transformation actually worked, and it worked fine, because all of those, we broke all of those rules, and we got all of those errors accumulated for us for free, basically, in like 3 lines of code, which would usually take probably 20 or something like that, right? And for a goodbye request, so once again, a name that is not over 20 chars, a date that is valid, and city that is once again not 20 chars, we get a 201 created. Okay, so that's it. Thank you for listening to me. Follow your books, criticisms, and ideas here. That's it. Thank you. If you have questions, please ask me right now.
Thank you very much, Oleg. As I can see, you don't have any questions. It was just only one, but you answered in the next part of the presentation, I think.
Yeah.
Okay, so are there any questions to Oleg? Okay, so it seems that we don't have any questions. If you will have any, I will provide contact details to Oleg in the chat. So thank you very much once again. And now it's time for Maciej. Wait. We can't hear you. You are muted. Okay, no.
Okay, can you see my screen now? First slide.
Yeah, everything works.
Right. Thank you. All right, so as I said before, my name is Maciej. I work at JetBrains in the Scala plugin team, but my today's talk will not be about that. It will be about something connected to my hobby of, trying to write a video game on JVM. It's about Cellular Automata, which is a form of artificial intelligence. And Aleksander's talk was very technical. My talk will not be almost technical at all. There will be some computer science and some algorithms, but very little actual code. So just relax and enjoy. We will talk for a moment about the history behind Cellular Automata. I need to I just need to say something about the most famous example. There's no way around it. So Conway's Game of Life will be there. There will be, although we will move to something more realistic, and that's weather prediction, where Cellular Automata can be used, or maybe it is even used, although I'm not sure about that. And then to the core of the presentation, that is how can we use that in video games for the non-player characters, in pathfinding and in decision making on some grander scale than just non-player characters. So, but first, what are Cellular Automata? And if you go to Wikipedia, you will read that Cellular Automata is a way to model complex processes by breaking them into sets of rules, applied again and again over time on data spread over a discrete lattice of cells. And these terms are important, that is, that there is some kind of logic, sets of rules that are applied over time. And a discrete lattice means a board, but that board does not have to be like a chessboard. It can be any kind of a 2D or 3D or even many multiple dimensional board that is composed of some kind of cells. So if we want to implement it in a programming language, let's say Scala, that would mean that we need a case class for a cell that models some data for a like kept in one cell, we need a board of those cells. We can model it by having a map. That is, for example, if we have a two-dimensional board, then that could be a map of identifiers from position 2D to a value that is that cell we just modeled. Then we need a concept of a neighborhood. A neighborhood are cells that are directly connected to the cell we are talking about. If we have we want to talk about the cell at the point 0, 0, then we have some ways to define the neighborhood. Two of the most popular are von Neumann, that is cells to the north, to west, south, and east of our original cell, or the Moore neighborhood, that is also northwest, southeast, but also the diagonals. But in real, this is not the only way we can define neighborhood. It can be more than that, it can be less than that, it can be something completely different as well. And there are rules. A rule can be defined in Scala as a function that takes a cell, and also probably will want to access the neighborhood of that cell, and it will create a new updated version of that original cell. And then we have a loop, which, well, we can really model it as an iterator of that map, of that board we have, to a new version of the map, where each cell in the new version of the map is a new cell that is created by the rules on the basis of the original cell and the neighborhood of that original cell. And we apply that, we just go and create new versions of the board as long as we like, to the moment where we have some kind of a result that we like, and then we can stop. Because of how it works, because Cellular Automata kind of motivate us to write code in a functional way. They are immutable. There are little cells of data, and there are rules that can be modified, can be modeled as functions of one argument to one result. Then I think it is very it fits very well the way we write code in Scala, but also you could, for example, use Kotlin plus the arrow library, which is like a functional companion to Kotlin. Also, the new versions of Java kind of go in the same direction, but probably we will have to wait until Java 30 or 40 or something like that. All right, history. So the guy who first came up with the idea of Cellular Automata was called John von Neumann. He was like a giant of computer science in the first half of the 20th century, and he did a lot for mathematics and the early computers. And just after the Second World War, he was so authoritative in the field that when he came up with this kind of a hobby idea of his, the whole academia decided that, okay, this is John von Neumann, he can do whatever he wants, so they just accepted it, and that was it. So the first, as far as I understand, Neumann was inspired by his colleague, a chemist or a biologist, who showed him the bacteria that replicated in a petri dish. And Neumann came up with an idea that if we have a goal to accomplish, we can do it with robots, and that if one robot is not enough to accomplish that goal, then that robot can take resources from the environment, can create copies of itself, and then those copies, together with the original robot, can try to accomplish the goal again. And if that's still not possible, then they can create even more copies of themselves. Not exactly what Cellular Automata are right now, but we are getting there. Then the idea was dropped for some time, until in the 70s, John Conway came up with his super popular thought experiment, or kind of a thing we do when we have time and nothing to do else. That is game of life. The first game of life, as far as I know, was played on the Go board because the Conway still didn't have his own computer. And game of life is, well, it works like that. We have a cell. This is something that I will repeat once and again in this talk, that we will have cell, we will have board, neighborhood, and rules, and the loop. So the cell is just a square that is alive, and we display an alive cell as black, or dead, and the dead cell is white. We have a board that is two-dimensional board of no matter what size. It can be infinite. And we have the move neighborhood. That means that we are looking for the neighbors of our cell to all the directions, vertical, horizontal, and diagonal. And the rules go like that. For any given cell, if the cell is dead, that is white, and in the neighborhood there are exactly three cells that are alive, that is black, then in the next iteration, that cell that is now dead will become alive. If the cell is alive, and in the neighborhood we have 2 or 3 cells that are alive, then in the next iteration, the cell will stay alive. And otherwise, if there are too many alive cells in the neighborhood, or if there is not enough alive cells in the neighborhood, then the cell will become dead, or if it is dead, then it will stay dead. You can think of it as a form of a fight for resources. If there is too many cells that are alive in the neighborhood, then the cell will die of starvation, but also the cell needs other cells to somehow interact with to live. So if there is no cells, no alive cells in the neighborhood, then it will die also. Just wanted to mention it. Just probably you know something about game of life, but it's important to keep it in mind when we will be going to more complicated examples. One thing, for example, that Cellular Automata can be used in more real life situations is weather prediction. And in weather prediction, it works like that we have a model of Earth, and we have the surface of Earth, that is our board, but we also need atmosphere. So we need 10, maybe 50 kilometers. So it's still three-dimensional board, but it's very flat. It's mostly surface and only a bit in the Z direction. And also you can see that this is a bit different than before, because the board is not flat completely. It's not infinite. It's a sphere. Some very weird things are happening at the poles. And then we create cells on that board by taking only a small cubes of size of, 1 kilometer, 5 kilometers, something like that, maybe a bit more, maybe a bit smaller. And in every cell, we can say, okay, this cell in the cell on the surface of Earth, or somewhere in the ocean, or somewhere in the atmosphere, we have certain temperature, we have certain humidity, we have some wind speed, if this is on not in the ocean. It has sunlight, it has some kind of a type of the area, like land, surface of the ocean, and so on. And we have neighborhood, which can be whatever we think is suited here, probably more, but also von Neumann, or something even more complicated. And of course, it needs to be 3D, because we are also interested of what's happening in somewhere higher and somewhere lower. And then we have rules, and the rules are our knowledge about climate and weather. So this is physics and a bit of biology. We know how we can use sun, like when the solar radiation can warm up the land, and then that land gives away that heat together with some with water, with humidity, and so on. So everything that we actually know how the weather can change, but only in this small area in one cell and in its neighborhood. And by applying those rules, like we can say, okay, if in this cell we have this temperature, this humidity right now, then by applying the knowledge we have, we can predict that, for example, next hour, the situation in our cell will be changed like that. And we do it for every cell in the world. And that is our one iteration. And then we take it, we create like a version of our world in an hour in the future. And then we apply it again and again and again. And this way we predict weather on any place in the world, or like the whole world together, because like everything is connected on our planet. And we do it for next day, next week, and so on. And that leads us to actually that can be skipped. And that leads us to actually the topic of how we teach cellular automata to make good predictions. And on one way, this is pretty straightforward. On another, this is more complicated than in case, for example, with artificial neural networks. For different reasons. Here we have like a small model that can, like on the top, you can see that we have a model that is in the past, and then during time it becomes something that is on the present. This is something we observe. For example, we can say that an hour ago the weather on the world looked like that. Then we wait an hour, and now we know how the weather on the world looks like right now. And we can use that to actually fine-tune our artificial intelligence, not only cellular automata, but also other types, in the way that we can model our world from the past. We can create that simulation, and then we can run the simulation that 1 hour to the future, to now, and we have a prediction, like our computer predicted how should the weather look right now. And then we compare the two. Like we know what the weather is, but we also know how the artificial intelligence thought that how it would look like. And there will be some kind of a difference between the two. And we can use that difference as a feedback, give it back to make changes to the rules, or to find out that maybe our data was not exact. We should get it better next time. And then we try it. We try to fix something, change something, and then we try again. How many times we need it to make the situation when the prediction is kinda similar enough to the present. And if it does, then we can run the simulation faster than the real time, and we can kind of trust that the prediction for the future will be actually pretty similar to what the future will bring, actually. There is a situation where this can be automatized, this feedback loop of comparison and then changes, because it is possible sometimes that the rules for the cellular automata can be given as polynomials. So in that case, the state of an automata in the next iteration will be some coefficient a multiplied by the state of the current state of the cell, plus the coefficient b multiplied by the state in the neighborhood, plus some coefficient c, for example. That's a very simplified version of it. And then we can say that our rules are really only those coefficients. And since they are only numbers, then we can use some kind of a automatic learning algorithm, like the Monte Carlo method, to modify the coefficients without our supervision. But quite often that is not possible. Quite often in cases where cellular automata can be used, actually what we need to do is to change the rules. And for changing the rules, like the real human being is necessary. Someone needs to sit down with the code and understand what's going on and fix it. There is, although, so it's not as automatized as in this, for example, in case of artificial neural networks, and where everything works pretty much just by saying, okay, this is not what we wanted, then like try to adjust the weights of the neurons by yourself and try to do it again. In case of Cellular Automata, we actually need to do it ourselves. We need to write better logic, but there is something that can help us. That is the rules for Cellular Automata tend to be pretty simple. We only talk about smaller, like a very small cubes, very small cells that have only some small amount of data, and there are only like a limited ways of changing it. So we have a good understanding of those underlying processes. And also, because we are talking here about cells on the in space, and we talk about changes in time, this is kind of intuitive, I would say. Like when we talk about other types of artificial intelligence, we often have this problem that this is very abstract, very counterintuitive. We need a lot of knowledge, and we need to be very careful about how we talk about it, and the process of understanding what another person is saying takes time. And yeah, in case of Cellular Automata, we often speak up in terms that we use in real life for real situations. So this is like the communication is easier. And we can, for example, use it also in video games, because video game is like a simplified, easy to understand version of the real world sometimes. For example, in 2006, I worked in a video game company where we used this old game engine called EX Jupiter that was used in the game Fear, which is like a first-person shooter connected, a bit horror-like. And we wanted to make a game that used the same engine for something a bit different. And one thing I remember that was really nice about it was how they solved the problem of teams of the non-playable characters, so the teams of villains, attacking the player. So that was not really Cellular Automata, but what they came up with can be easily modeled as Cellular Automata. So here, for example, we have a room where we are that sheriff there on the field A. The sheriff, we just came into the room with our gun. And we know there are villains, but they are on the other side of the wall. There are 3 villains on the field E, and they want to attack us. They can attack us from 2 sides. So one of them can go to the field B, the other can go to the field C, and they can start shooting at us. The thing is, we don't want them all, like we as the computer, as the artificial intelligence doesn't want them to all go only from one direction. They want them to spread out, attack from both sides. And also, if one of the villains is killed, then the other should also go and take place that killed one. The one that is that green one, for example, that is a spare, shouldn't go on the direction from the side that is already taken by the villain who still lives. So how can we do that? First, again, we can model a cell, and a cell should know if there is a player in the cell. And the cell should also know what villains it has, and if those villains are tagged and untagged. Being tagged means that, okay, this villain already knows what to do. We already computed the path which that villain should take. And also, every cell should have like a path to the player. So what is the shortest path from the given cell to the cell where the player is right now? And then we can apply some rules. For example, for every cell, we check if there is a plier in that cell. And if there is a plier, then okay, we don't have to do anything about that cell. Then, if there is no plier in the cell, but there is a plier in the neighborhood, so for example, for the field B, the neighborhood here is the field D and A, and we see that, okay, on the field A there is a plier, then what we can do is to create a path from B to A. So if villain will happen to be on the field B, then the villain will know that, okay, to go to the plier, they need to go to the field A. And then we have another rule. If we are on the cell, if we compute the state in the next iteration of a cell that has no plier and also no plier in the neighborhood, then maybe it is possible that the cell in the neighborhood has a path to the plier. And that is, like you can see, some kind of a recursion. If we don't have a plier in the neighborhood, but a cell next to us has a path to the plier, then we just take that path, add our cell, and then we create this way. We can create a longer path from the cell, for example, D, through B to the plier. And then at the end, if there are some villains that are not yet assigned tasks, they are not tagged, and we have a path to the plier. For example, on the field E, we will actually have two paths, one going DBA and the second going FCA. Then we can take at random one of those villains without the task and give them a task. Go this way or go this way and attack the plier. And this is, I don't have a slide that would like show how it exactly work out, but you can imagine that if one of the villains goes to B and starts shooting, the other villain goes to C and starts shooting, and if the player kills one of the villains, then what happens then is that, again, one of the paths is not tagged, and the villain that stays at E, which wasn't assigned any task because all the paths were already taken, suddenly have a free path. So this villain, again, when the Cellular Automata would, when the engine of Cellular Automata will work, will take that path and replace that killed villain at the point B and will start shooting at the plier. Another thing that is important here to take away is that we have in every time we use a game engine, we have some kind of a main loop, and that main loop takes care of the movement and the graphics and the physics and so on. But this is not the same as the iteration of Cellular Automata. It's not like one iteration of the game is one iteration of Cellular Automata. Actually, it should be done this way that, for example, every, 120 iterations of the game state, that game is giving its update to the Cellular Automata engine, like a separate library somewhere there. And then that Cellular Automata starts to work its own iterations up to the point where some decisions are made. And then those decisions are given back to the game. The game applies those decisions and again works for a given number of turns, and then again update the Cellular Automata. So these are two separate things. All right, here you can see an old game that can be also written this way. We can have the Pac-Man that tries to eat the points and also needs to avoid the ghosts, but the ghosts can find the path to Pac-Man and also can try to surround Pac-Man from all the possible directions instead of just following him from one direction. Original Pac-Man sadly wasn't done with Cellular Automata, but it could be. Okay, so but one thing we talked about for a moment before was that there are paths, right? We can use Cellular Automata to actually make paths to certain points on the board, and that is something that can be abstracted to a higher level and use in more interesting ways than just by leading villains to the player. But first, let's talk about some kind of a typical sequential path-finding algorithm, breadth first search, and that is pretty. That looks like that. We need a queue. We have points that are like only positions on the board, and we create a queue that will take a point and then give it back away again. We take the first point in the queue is our starting point. We put it in, we take it back immediately, and for every point on the which we take, we check if this is the endpoint. Well, if the start point is the endpoint, then we are done, but this is not the case here. If this is not the endpoint, then we take the neighborhood of that point. For example, all those 8 points around the starting point, and we put them in the queue. And because our point is not the endpoint, then we discard it, and we take again the first point in the queue. So, for example, if now a starting point is 0, 0, then what we do is we take the points 1, 0, 0, 1, minus 1, 0, 0, minus 1. We put them in the queue. We decide that 0, 0 is not our endpoint, and then we take the first one from the queue, which is 1, 0, and then we look again. Okay, so 1, 1 is also in the neighborhood now. 2, 0 is in the neighborhood. 1, 1, minus 1 is in the neighborhood. 0, 0 was already there, so we can ignore it. And this way, we create something like a spiral that goes from the starting point outward, and at some point, after many of such iterations, that spiral will eventually hit the endpoint, and then because we remember from which point we went to which point, then we will have our path to the endpoint. So, but you can see this is sequential. Every point on the board is treated one after another. If we do the same with Cellular Automata, that could be much quicker. We also can use, well, in this case, we can use von Neumann. We can also use Moore, which would be probably a bit faster, but let's keep it simple. And this is distributed. So one thing to keep in mind is that every cell in the board is, at least ideally, is computed at the same time. We don't need to do it sequentially. There's nothing that would interact with processing one of the cells. So we can just distribute them over all the threads, all the CPUs we have, and for every point for every cell, we only need information about that cell and about its neighborhood. So the cell, this can be a bit counterintuitive because we will be actually looking for the path to the starting point, not to the ending point. Like first what we do is we check if we are at the start point, and if yes, then we say, okay, this is the path to the start point with just one cell. And if it is not the start point, then we say, okay, we have empty path. We don't know yet where we are. We don't know yet what is the path to the start point. And then if we already have path, so if this is the start point, then we do nothing. And as in the case of the example with villains and the sheriff, we also we also do nothing when there is nothing around us that would tell us that there is a path. But if there is like a cell in our neighborhood that has a path already, then we take that path. Or if there are many more than one path, then we take the shortest of them, and we add our cell that we are right now at. And And if the cell is the endpoint, then we finish. We give that path to the game. We also need to revert it, but that's just a trivial technicality. And if not, then we repeat that procedure. So instead of going sequentially in a spiral, we go in every iteration. We go by calculating the whole board, and in the first iteration we will update the first 8 here. Then in the second iteration we will update, well, however many there is in the one square over it, then over it, and so on and so on. So we will, in a kind of similar way, we will find that path from the endpoint to the start point, and then we will revert it to get the path from the start point to the endpoint. But in reality, in practice, it will be much faster than in case of sequential path finding. So again, how to say that? Pathfinding is interesting in its own. Like, we can, this way, in video games and in other situations, we can use pathfinding for many important things, like actually finding paths between ourselves and some other place. But again, we can rise it up to the next level of abstraction and think of it as a way of making this chains of decisions. Like, imagine that what you have as your cell is the state of the whole world in a video game. So it's like simplified. It doesn't have to be the real world. And then if one cell is the whole state of the world, then the neighborhood cells just next to it, directly connected, is the state of the world that can be achieved with only one action. So in a game, it can be, I don't know, attacking someone or making some changes, like building a building. Okay, building a building, right? Something like that. Like, one thing you do, one click, you make one decision, it takes one turn, and you are at that new state of the world. Then the board, the whole board, can be a graph of connected states, of connected cells. Then that board is like amorphous. Like, you can, it doesn't matter if this is no longer 2D or 3D or whatever. It's just like a infinite graph of all possible states of the world, and they are connected. The edges of that graph are how you can go from one state of the world to the other state of the world. So in the other worlds, it is every edge is one action that can make you go from this state to that state. And if you imagine, like, the whole world and all the possible actions like that, then basically making a decision, if you have like a place somewhere where is your current state, and there is a place, there's some state of the world that you want to achieve, like, then the rules how to create a chain of decisions that will lead you from the current state to the desired state are basically pathfinding in that big graph. So again, an example, this time from a real video game. This is Europa Universalis 3, and let's say we are the Polish state, and what we want is to invade the Czech. And Polish state, for example, in the current state, is we don't have money, we don't have soldiers, but what we want is to invade Czech state. So what we need to do, for example, is to run such a cellular automata-based pathfinding algorithm, and we want to find a way. And that way can be, for example, one action would be to raise taxes. And when we have money from those taxes, we can hire soldiers. And when we hire soldiers, we can attack Czech state, and then we can conquer it. In reality, please don't conquer Czech. They are very nice people, but in theory, this is how we can do it. All right. Technically, I don't have much time more, so I just want to say that, as I said before, because we calculate every cell in locality, like we don't need to know the whole state of the whole board to calculate one cell. We only need to know the state of the cell, the current state, and we need to know the current state of neighborhood. Then it is very fitting to do it on the GPU. So we can use NVIDIA CUDA. We can also use OpenCL available on JVM to create small packets of data from the current state of the cell that models something we want, and also the data from the neighboring cells. We can put that on the GPU for every of our cells. And we can then run it on GPU, we can get results, we can create a new version, a new iteration of the board from those, and then we can do it again and again, taking advantage of that we have a GPU and those standards. If you would like to do it, especially in the context of video games, there is this very nice small library, actually called Lightweight Java Game Library. This is basically like a thin layer over C libraries like OpenGL and OpenCL that allows us to use GPU. But it's only like a thin layer over it. If you actually want to write a video game, then it would be probably better if you, on JVM, you can use one of the, these two game engines, libgdx or JMonkey engine. libgdx is better for 2D games and Android games. JMonkey engine is better for 3D games. There are a few others as well. You can search for them. And yeah, so that was probably quite a bit. So I wanted to summarize at the end. Cellular automata are a great way to model complex dynamic systems in 2D space, 3D space, but also in multidimensional space. This is not a way to build anything that can probably give you a good job. You will not build a backend, you will not build even a graphical user interface. And it is not a kind of an artificial intelligence that will find a cat or a tank or whatever on a photo. But it is useful to simulate complex systems. It is useful to simulate state of a video game. It can predict future behavior also in a video game or in real world, like predicting weather. And it is well suited for distributed computing. It allows for very quick pathfinding, decision-making in some specific context, not all. And it enables us to think about logic of artificial intelligence in simple, intuitive ways, which is certainly good, like if you just want to write a video game and have some simple artificial intelligence in it. So thank you. I have a repository at GitHub where I play with it a bit. Now it's a bit dusty, but I want to refresh it this year and actually use in my bigger project of writing a video game on JVM. Right now you can look at it for playing some Game of Life, Langton's Ant, which is another known cellular automata, and also the game of Snake. And, well, you can also find me on Twitter.
Thank you, Maciek. Thank you very much. Well, guys, do you have any questions to Maciek? We have some delays, but I don't see any questions. Well, so thank you very much for both presentations. And of course, I will also send contact details to Maciek if you would like to ask him, I don't know, maybe more questions after the meeting. You can do so. So thank you very much once again, and thank you all for joining us today. Thanks.